Hello everyone, welcome to day 14 of Advent of Code. I'm recording this intro afterwards, and I have to say, today's problem was lovely. Part 1 was a straightforward simulation which we just coded up and then made a pretty visualization for. Then part 2 was basically just do part 1 1 billion times. We had to be a bit clever about this, but Livebook made exploring the problem very easy, and then writing it up was straightforward. As always, this video has chapters so that you can skip around, and the link to the code is in the description below. Now, without further ado, let's get started. Day 14. Parabolic reflector dish. Because this is going to be another thing that has absolutely nothing to do with saving Christmas, isn't it? Yep. Okay. Let's slog through this. You reached the place where all of the mirrors were pointing, a massive parabolic reflector dish attached to the side of another large mountain. This is after we made it through the desert of mirrors. There is now a parabolic reflector dish, whatever that is. The dish is made up of many small mirrors, but while the mirrors themselves are roughly in the shape of a parabolic reflector dish, each individual mirror seems to be pointing in a slightly wrong direction. If the dish is meant to focus light, all it's doing right now is sending it in a vague direction. This system must be what provides the energy for the lava. If you focus the reflector dish, maybe you can go where it's pointing and use the light to fix the lava production. As a reminder, we're trying to fix the lava production so that the machines on Machine Island can work, so that we can fix the sand machine with sand we need in order to filter the water for the snow machine. Upon closer inspection, the individual mirrors each appear to be connected via an elaborate system of ropes and pulleys to a large metal platform below the dish. The platform is covered in large rocks of various shapes. Depending on their position, the weight of the rocks deforms the platform, and the shape of the platform controls which ropes move and ultimately focus the dish. In short, if you move the rocks, you can move the dish. The platform even has a control panel on the side that lets you tilt it in one of 4 directions. The rounded rocks 0 will roll when the platform is tilted, while the cube-shaped rocks will stay in place. You note the position of all of the empty spaces, dot, and rocks, your puzzle input. For example, wait a second. So, the individual mirrors each appear to be connected via an elaborate system of ropes and pulleys to a large metal platform below the dish. So all of the mirrors are connected to this one large platform. The platform is covered in large rocks, and the rocks will be rolling around, presumably. Depending on their position, the weight of the rocks deforms the platform, and the shape of the platform controls which ropes move. Okay, so we have to move the rocks across this platform to do something to the mirror. Start by tilting the lever so all the rocks will slide north as far as they go. Okay, so we have 4 rocks on the first column, then 1, 2, 3, 3 rocks on the second column, one rock above on the 4th column, and then 2 more rocks get blocked by the cubes, by this cube here. You notice that the support beams along the north side of the platform are damaged. To ensure the platform doesn't collapse, you should calculate the total load on the north support beams. The amount of load caused by a single rounded rock is equal to the number of rows from the rock to the south edge of the platform, including the row the rock is on. Cube-shaped rocks don't contribute to the load. So the amount of load caused by each rock in each row is as follows. The amount of load caused by a single rock is equal to the number of rows from the rock to the south edge of the platform. So this is basically the 10th row from the bottom, so every one of these rocks has a load of 10. So the total load is the sum of the load caused by all of the rounded rocks. In this example, the load is 136. Tilt the platform so that the rounded rocks all roll north. Afterward, what is the total load on the north support beams? Okay, part 1 seems fairly straightforward. I assume there's going to be something about tilting the platform in other directions in part 2. What does our what does our full input look like? Okay, it's a largish grid, but we can just simulate this. We don't need to do anything clever here. Yeah, we can just simulate all of the rocks falling north. Or rather, rolling north. So, again, what do we have to do? We have to roll all of the rocks north. Here we go. Start by tilting the lever so that all the rocks will slide north. And then, what is the total load on the north support beams? How do we represent our data? How do we represent our data so that we can calculate this easily? We can just have a map from rock to its coordinates. And then we can have a second map for the cubes, which impede movement. But then for every rock, we'll want to know how far. For every rock, we'll want to know how far it can roll. So really what we want is the location of the cube on the same column as it. The location of the cube on the same column as it. And we can sort of assume that there's a row of cubes at -1, or just above our playing field, which is what prevents all the rocks from rolling off the platform. We could do something clever here where because really what we want is for every column, we want the list of cubes on that column. And then we want to binary search into that list with our rock coordinates so that we can efficiently determine which is the cube that is just before our rock. But given the size of the input, we don't really need to do anything clever. We just need to simulate this. So yeah, we're going to store two maps. One thing that maps the rock to its coordinates and another one that maps the cubes to their coordinates. And then we're just going to linearly search through this essentially. In fact, we could optimize this a bit and not have a map and just have everything stored by column. But that will probably cross over on part 2, where we'll certainly need to do stuff with left and right. Okay, let's get going. We're solving this in Livebook. We start by creating a new notebook. Today is day 14. Like always, we have to start by adding Kino as a dependency. We'll be using Kino to read our input and display more complicated outputs. We will probably actually need a visualization because printing this as a string is going to look horrible. Yeah, we can just generate an SVG for this. Okay, this first section is going to be called inputs. Then we have our example input, Kino input text area. And we're going to have a second input for our full Kino input text area. Full input. So Kino input text area generates a text area, and then we'll be able to read it later by doing Kino input read of example. So this is our example, and this is our full input. Now we create a new block and call it part 1, and let's parse our input. So first off, Kino input read example. This gives us the whole example as a long string with new lines in the middle. So let's separate the new lines. Okay, now we have a list of lines, except we also have an empty string at the end because of the new line at the end of the input. So we trim to get rid of it. Okay. Now I said we want to parse this into a map because we'll be working on coordinates. In order to do that, first we need to add some indices. So enum with index. Now each line is annotated with its index. We enum map over it. It's going to be called line and I. Okay. Each line we're going to... What are we going to do? Is this a enum map? Yeah, let's do an enum map. So we start with line, then we convert it into a char list so that we can iterate over it easily. Then we do enum map. Then we do another enum with index to annotate each character with its column. Now we do enum map. So we have a character and the J. And now what? Now we actually want to build two maps, don't we? Actually, first off, let's just output character I and J. Let's see that this works. Looks like it did. Now we want to do something special for O's, dots, and hashes. So, case ch do. If it's a dot, we do absolutely nothing. So let's return nil for now, and we'll figure this out. We'll figure out what else we do later. Now if we get an O or a hash, we want to add it to one of two maps, but we don't have two maps. So instead of a map here, let's do a reduce. And the accumulator is going to be two different maps. And here, we also take our two accumulators. The first one is going to be called rocks, and the second one is going to be called cubes. It's a bit unfortunate that today's problem has both rocks and cube-shaped rocks. Okay, line. This map here is going to be a second reduce, and it takes rocks and cubes. Then at each step, it takes rocks and cubes. And then here, for CH, we just do rocks and cubes. We don't change our accumulators at all. If we get an O, we have to add to rocks. So it's map.put rocks at I and J. And in fact, it's not really a map, is it? It's a set. Yes, it's a set. So this is mapset.new, and this is mapset.new. Although I do want to give names to the rocks. Well, maybe later. Okay, so mapset put. And then the cubes are completely unchanged here. And if we get a hash, then we add to the other one. And cubes I and J. Okay, and if we run this, it should give us, where is it? Mapset new. Add arity. One too many curly brackets here, and one too many curly brackets here as well. Okay, now we should get two sets. One of them is the rocks, the other one is the cubes. This is actually correct. So we have, this is rocks. We have 0, 1, 2, 3, and 7. 0, 1, 2, 3, and 7. Okay. And on the first line, we have just one cube on 9. Now on 5, this is 4 and this is 5. Right? 0, 1, 2, 3, 4, 5. Okay, this works. Now that we have this, actually I want a function that prints out something, that prints this out, because we're going to be modifying it and it's going to be a pain to debug if we don't have a print function. So, def module part 1. Def print board. Actually, here I want to name these two maps. I don't want to be passing around a tuple. So this is going to be a map, and this is going to be called rocks. This is going to be called cubes. Here we don't need to name them anymore. This is, let's just call it accumulator. Here as well. This is accumulator. This is accumulator. This is accumulator. And here we just use the map updating syntax. So it's accumulator and rocks becomes this. Here we use the map updating syntax again. So this is ACK and cubes becomes this. Where? Line 15. Okay, now we have the cubes and the rocks. Now we can print the board. This will take as input a map of rocks and cubes. We really need the maximums, don't we? Yes. So here we also need to somehow add, let's call this lines. So here, where we start, we also do, what do you call it? Lines is length of lines. So this is how tall our board is. And I also want columns, which is going to be the string length of the first line. Right, and now we can see we have 10 lines and 10 columns. Good. Let's split this across multiple lines for readability. Now here we also take lines and columns. In fact, since we take basically everything, let's just get this as a map and not to deconstruct it. Right. And now here we go from 0 to data.lines -1. Then we do an enum map. we just go to enum, we just iterate through data lines. It was correct. We enumerate through the indices. And now for each index, we are going to print something. We also need to, for each line, we need to also enumerate from 0 to data.columns -1. And after this, we're going to need an IOPutS to output a new line. Right. Now for each I and j, we have to check if the thing is in rocks, if it's in cubes or not. So this is cond do I and j in data.rocks. So if it's in rocks, we output a big O. And if it's in cubes, we output a hash. And otherwise, we don't output anything. We output a space. Okay, so now if I pipe this into enum, it's not enum, it's just one entry. Yes, okay. So if I pipe this into part1 print board, we should get a printout of something. Right here, it's not putS, it's write, because putS always adds a new line at the end. Now I see here that I copied the input after it was modified. So we want to actually start with this. Okay. So we have, let's return an OK here. Yeah, let's return an OK here so that we don't pollute our output. Okay, so we can read the board and we can print it back out. Now we actually need to move all of the rocks up. It's going to be a function. It's going to be called tilt north. Tilt north? Yeah, let's call it tilt north. It's going to take one of these. It's going to take our data as input and output our data again so that we can print it out. And now we just have to figure out how to do this. I always write the parameters like this so that we make sure we receive a map as our input. Like Elixir is not particularly strongly typed, so there's always a chance we'll screw up and give the function some completely wrong data type. But if we do it like this, then Elixir will fail fast when it receives something that isn't a map. Okay, tilt north. We have to iterate over all of the rocks and then do something with them. Before that, just going to quickly reload this. All right, so we iterate over all the rocks. And then what do we do? This is going to be a reduce. So one slight problem here is that we need to keep track of which other rocks we've modified before. Right, so here, if we move this rock up, then move this rock, then the third rock can only go up to the third row. It can't go any further up. That's annoying. Okay, I think I need more data. Let's just make this return data and unchanged. could do this the actual other way around and start with the spaces and see if there's any rock to fall into that space. Would that be better? Well, that would let us iterate fairly easily over everything, because we'd just be iterating over the spaces. But it would prevent us from doing any optimizations later. Well, let's write it. Let's see what happens. And then worst case, in part 2, we have to do something more complicated. Because if we don't do, going over the spaces is nice, because the spaces are sort of static. Like if we see an empty space, we know there might be a rock that could fall into that space. So we can just search for the rock that has to be moved there and move the rock. If we do it over rocks, though, we don't actually have identifiers for rock, given that we're using a set. If we use the map and generated the unique identifier for each rock, then we could do other stuff. But yeah, let's do it with spaces. So this is going to be basically a cubic algorithm. We're going to go over each cell in our grid, and then we're going to search vertically for a rock that could fall into that location. So we do 0 to data dot lines minus 1 again. This is going to be an enum reduce, and it's going to be modifying data. And it takes I and data. Then we're going to do another enumeration from 0 to data dot columns minus 1. And this is another reduce that modifies data. Now we have to do an if, right? If I and j are not in data.rocks and I and j not in data.cubes, then we are going to do something. Otherwise, we just leave data unchanged. Yes, so this is the space case. This is where we're going to modify our data. If we found a space, a cube, or a rock, then we're done. We don't have to do anything here because the space is occupied. So here we have a space. Next up, we need to do another iteration. It's going to start from, we're doing it vertically, so it's going to start from j plus 1. And it's going to go to data.columns minus 1. And in fact, this has to go to data.columns minus 2. No, columns. We start from I plus 1, and then we go to data.lines minus 1. And here, at the very top, we actually have to do our first iteration from 0 to data lines minus 2, because we won't be able to move anything into the top, into empty spaces on the bottom line. So, we have an iteration here. Let's call this k. It's another reduce, so it takes k and data. Now really what I want is something that sounds like reduce until. Is there a reduce until? Reduce while. Reduces enumerable until function returns halt term. The value for fun is expected to be cont ACK to continue the reduction with ACK as the new accumulator, or halt ACK to halt the reduction. If func returns halt ACK, the reduction is halted and the function returns ACK. Otherwise, the enumerable is exhausted and the function returns the accumulator of the last cont ACK. Okay, so this is what we want. We want reduce while. So what happens? What do we do here? If k and j are in data.cubes, so if we've encountered a cube, that means we stop because there's nothing that can fall over the cube. So we return halt data, right? It's halt and cont. We return halt data. And here we're going to do multiple conditions, so let's do a cont. Halt and data. Okay. If k and j are in data.rocks, then we're going to do something more complicated. And otherwise, we're just going to continue the iteration. So we're going to here do cont of data. Right, now, k and j, so we found the rock. We found the rock that we can move into our current location. So we're going to return data with the rocks modified, and only the rocks modified. And what's the modification going to be? It will be rocks pass through map. Let's write this on multiple lines. Rocks. So we pipe rocks through map set delete data.rocks. Now we have rocks already. We delete, what do we delete? We delete k and j. We deleted the rock that we found. And then we add the rock at the location where we currently were, which is I and j. And that's it. Here we have data.rocks. No function clause matching. Okay, so I screwed something up. Tempted. Wait, what? Enumerable func act. Oh, halt. Right here, where is it? We have to return. We don't return just the accumulator, we return cont accumulator. Right, and now is this what we were expecting? All of the rocks moved up to the top. How do I check this easily? So there's basically a little pyramid here. Let's close this. There isn't. I lost a rock on the second position here. Right? There should be 4 rocks, but there are not 4 rocks. Was it parsing the input correctly? It was. So here, definitely lost a rock. Let's actually print the original board here. Oh, I know how to do this better. Part 1 print board here. Where are we? Here. Part 1 print board. Instead of returning OK, let's return the data. And now we can just add our print boards in the middle. So now this should print 2 boards, which is almost nice. Let's also print some space. So after our whole iteration here, let's do another putS. Okay, so now we can see our original board and our, whatever you call, our tilted board. And let's also return OK. Get rid of that output. Okay. So we did not correctly move rocks up. Why not? Well, let's output something. IO put this. Rock rolling from inspect I and j to inspect I and j, and it was rolling from k and j to I and j. And now we can actually see rolling from 1 1 to 0 1. That's incorrect, because there's already something on 0 1. No? What do you mean rolling from 1 1 to 0 1? This is 1 1. And this is 0 1. K and J, not J and J. That explains the confusion. Okay, rolling from 3 1 to 0 1. 0. Rolling from 3 1 to 0 1. 3 1 to 0 1. This is correct. From 4 1 to 0 1. Okay, this is clearly wrong now. And indeed, it ate. Right, it. Okay, so it tried to roll two things onto the same location. It rolled two things onto the same I and J. Here, it's not cont, it's halt. Because once we've rolled the rock to a location, we can't roll anymore. Okay, this looks much better. We have our little pyramid here. Then we have a rock stuck after the cube here. Then a couple of rocks stuck after the cubes there. Yep, rocks stuck here and here. And okay, so we now have our board. Let's comment out this IO print s, this IO put s, yeah. So now we have to compute, what was it again? The strain, right? The total load on the north support beams. So we just have to go over all of our rocks and compute their weight based on their lines minus I value. Right, so let's pipe this into a new function. The new function is going to be called compute load. That compute load. We again take our data as an argument. We have to compute something over all of the rocks, so this is going to be an enum. So we iterate over all the rocks. This is an enum map fn I and j. This is the coordinates of the rock. Let's just say 0, and then this is going to be piped into enum sum, since we're summing up. And the thing we compute for each rock is, it doesn't, we don't care about the column, we just care about data.lines minus I. So how far is it from the very bottom edge? So the rocks at the top column are going to be have I 0, and lines is 10, so it will be 10 as needed. Okay, now we don't output OK anymore. We output 136. All right, this works. Let's try it on full. 106,648. 106,648. Is it loading? It is loading. Did I crash Advent of Code? Da 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 da. Okay, in the meantime, yeah, I don't really like this massive print. Yeah, this is unreadable. If we have to debug this, we're going to have problems. So we're going to create a new section called visualization. Yeah, and then we're probably going to move this somewhere further up. Def module this. We have to do everything in modules because Elixir doesn't like top-level functions. And we're going to take our little print board. We're going to take our print board function and modify it so that it outputs an SVG. And while we're at it, let's also move this whole thing into an input parsing function. So this whole thing is going to be called read input. And this takes as an argument a Kino input. Then it does this whole thing from before. So have to indent this. And it returns our little data structure. Here we can replace all of this with read input full. Part 1, read input full. Gateway timeout. Well, that's not my fault. I didn't break it. I hope. So if I run this, it should still work. No. Undefined variable full. Right. Here, when we read the input, since we're in a function, now this is called input. Okay, and we get our answer back. It does load, the page loads now, so 106,648. 106,648. That's the right answer. You are one gold star closer to restoring snow operations. Okay, so that's it for part 1. But before continuing with part 2, I don't even want to see the problem statement. Let's do our nice printout. So here, we're doing this. Part 1, read input, let's say example for now, and then we pipe this into viz print board. And this works as expected. But now I want print board to do more complicated things. It will eventually generate an SVG, and yeah, actually we should just start by generating an SVG. I figured out how to do this a few days ago. Here we go. So I'm just going to copy chunks of this. Localhost, where's my Livebook? I want both of them open at the same time. Make this bigger, and we're updating our visualization. Let's leave print board alone, and let's do def draw board. Now, does Livebook's copy thing work from one Livebook to the other? I'm going to guess no. Yep, no. Okay, so I'm going to copy this from Emacs. HEX something something. Yeah. I'm doing this from Emacs because Livebook's whole Livebook's V simulation thing kind of breaks down if you try to copy paste stuff into it. Okay. This copy paste at least. Now here, let's fix the indentation. This was done after that one. I wrote this after that one problem with the universe and the galaxies. So this is why this is all referencing stars. Reload this to get rid of the bug. Okay. I need to import Phoenix component here. Phoenix component is the thing that gives us the sigil H thing that we need in order to generate HEX. Right. And I need to add Phoenix Live View as a dependency. Okay. Now it should work. Yes, but now if I do, instead of print board, draw board, it should draw to my little starscape. If I do draw board and then pipe it into Kino shorts HTML, and this prints out my starscape. But instead of starscape, I want our little playing board. So we're going to do that here. How do we do this? We're going to do 2 for loops. I mean, we're basically going to replicate this, but in the SVG generator. And actually, we don't need to replicate this because SVG is blank by default. So we can just go over all of the rocks and then over all of the cubes. So let's print, let's start with cube. Cube 4. This is going to take an I and a J, and it's going to come from data.cubes. And we're then going to pass I and J as arguments to the template. Where are we here? Assigns. Instead of stars, we're going to do data. We're going to send data to our template. And we don't need stars anymore. We probably need dim, since that's just dimension meddling with the dimensions. And we don't need circle anymore. This is now called cube. And this is going to be a rect. The fill is... What's the fill for the rocks going to be? It's going to be a fairly dark gray. The opacity is unchanged. And then we have to specify x. X is going to be I times something. X is going to be I times dim divided by, let's call this, what? Side. And we're going to pass side later. Y is going to be J I times side. And X is actually J times side. And then we have width and height. Width is just going to be side. And height is going to be side again. And here, side is going to be 600, which is the width of our canvas, divided by data.lines. Divided by max of data.lines and data.columns. In case we have boards that aren't perfect squares. And then, where is it? Here. Let's pass side as well to the template. And we need to pass side in as well here. Undefined variable j. Right, we need an @ sign because we're getting this from the assigns. And this gives us This, what is this? This gives us just the rocks, just the cubes. So now we do the same thing for the rocks. And the fill for the rocks is going to be a much lighter color. Let's say CCC. And this is called rocks. Okay. But honestly, having the edge here, the edge looked nice when we had a starscape, but it's a bit confusing. Yeah, it's a bit confusing. So let's draw another rectangle. Can I do this? What happens if I do a stroke and then, I don't know, red? Let's look at what SVG, how SVG works. What I want here to see is what are the parameters we can pass to a rect. Surely there's stroke width or something. So stroke. What's stroke? Stroke is the attribute. Yeah. Stroke is the color. But how do I specify the width of the stroke? So, line cap, line join, stroke width. Here. I want, let's split this across multiple lines. No, actually, no, this one's fine. This is just the rocks. The one I want to split it across multiple lines is maybe this one. Okay, stroke, width. 5. Okay, now we have a little red border, but I wanted this to actually surround the display area. So 0, 0, and width minus 100 and height minus 100. Or rather dim. Right, this is literally dim. Okay, and it's cutting off a bit. So actually this starts, so let's make the stroke width 4, and then it goes from -2, -2, and then dim +2, and height is also dim +2. And now I'm hoping it completely surrounds our board, yes. Okay, so these are our... This doesn't look right. The rocks should be circles. And then we have the circle X, circle Y, and instead of width we have radius. So the radius is going to be psi divided by 2. And these are off-center now because we're specifying the center coordinate. So this is j plus 0.5 and I plus 0.5. Okay, so now we have our board. And if we do, what was it? Part 1, tilt north. This should now draw our board with everything moved north. Yes, so this is much more readable. Ish. Let's see how this does on the full example, on the full input. Well, this is readable. Yeah, this is actually readable as opposed to whatever the hell this is. And now if we do tilt north, we can even see that it kind of looks correct, right? We can actually see that everything moved north as expected. And we see that there's no funny business going on with the rocks sort of sliding left or right. Yeah, this is nice. And this might also be the thumbnail. Okay, back to the actual problem statement. What's part 2? Part 2. the parabolic reflector dish deforms, but not in a way that focuses the beam. To do that, you'll need to move the rocks to the edges of the platform. Fortunately, a button on the side of the control panel labeled Spin Cycle attempts to do just that. Each cycle tilts the platform 4 times so that the rounded rocks roll north, then west, then south, then east. After each tilt, the rounded rocks roll as far as they can before the platform tilts in the next direction. After one cycle, the platform will have finished rolling the rocks in those 4 directions in that order. So it's north, west, south, and east, so counterclockwise. Here's what happens in the example above after each of the first few cycles. This process should work if you leave it running long enough, but you're still worried about the north support beams. To make sure they'll survive for a while, we need to calculate the total load on the north support beams after 1 billion cycles. In the above example, after 1 billion cycles, the total load on the north support beams is 64. Run the spin cycle for 1 billion cycles. Afterward, what is the total load on the north support beams? Okay, this is going to be slow as hell if we try it with our code. Probably. Well, first thing, I just want to implement the slow version of the code, tilting in all 4 directions. Because that will at least give us something to test against. And then I'm curious to see how long all of the cycles take, by how many cycles per second we can actually process with the slow code. So, back to here. Let's switch back to example. The slightly annoying thing about our tilt north function is that it's very specific to tilting north. It wouldn't work on in any other direction. Or would it? Because really the only thing that would change, if our direction changed, really all that changes is these 3 ranges. If we change the 3 ranges, then we can tilt in any direction. And in fact, yeah, so we always have a range along the primary axis, then a range along the secondary axis, then a third range along the primary axis. So we basically have 2 axes. And I and j are always the same. It's just that the actual parameters here might change, right? So this is the thing that changes, both the range and the actual reduce call. Right, because it can also be here that we have j and k instead of k and j if we're doing it along the other axis. How do we write this? How do we write this? Or how do we write this without copy-pasting the code 4 times? For starters, let's get rid of all of these manual tuple constructions here. Let's write them only once. So here, k and j is going to be so actually lock is going to be I and j, and other lock is going to be k and j. And then here, if other lock is in cubes, other lock is in rocks, Then we delete other lock and put it in lock. And this lock here is actually generated at this location, at this point here. So it's not ij, it's lock in data rocks and lock in data cubes. If I run this, everything is unchanged, yes. So let's leave this code unchanged and write a more generic version of this. Let's call it tilt. And this one is going to be tilt north original. In fact, we kind of need 2 copies of this. This one, or rather, this is going to be called tilt. Then here we're going to have reduce primary. And instead of going from 0 to data lines, we're going to call reduce primary with data and then fn I. Is it I? Yeah, it's I. So this is reduce primary. Instead of I, actually let's call it primary. Then here, instead of this, we have reduce cross, which is data, and then cross. And here we get rid of that. Reduce cross is going to be our next argument. Now we actually need to make lock somehow. Lock is going to be 2 coordinates of primary and cross. The 2 coordinate is going to be our third argument. And since these are going to be lambdas, probably we have to use, since these are going to be closures, we have to use Elixir's special syntax for calling closures, which is dot open parentheses. Okay, now if lock is not in rocks or in cubes, then this is going to be another reduce cross. This is going to be a reduce primary data, and this one starts from 1. So this one here starts from primary plus 1. Then it does, and then we have other primary. Okay, and our other lock here is going to be 2 chord of other primary and cross. And then other lock, this is correct, this is correct. Okay, so now we just have to write tilt north we have to write our new tilt north using this tilt function here, and then see if it works. So tilt north, it just takes the data as an argument. It just calls tilt with the data and fn, reduce primary. Reduce primary has to look like this. How does it know where to stop? It doesn't know whether we're doing lines or columns. So reduce primary actually needs, oh no, here we do know. But reduce primary takes a data, then it takes a start, and then it takes what? An inner f. And it will do start to data.lines minus 2, because this is our tilt north function. This will pipe into enum reduce. Enum reduce data, and then inner f, right? It's just Reduce primary. Oh, here we definitely need data as well as an argument. Elixir always puts the accumulator on the second position, so this is data, data, and one more data here. Okay, so tilt. It takes the data, it takes the inner f, then it calls reduce on. It uses data as an accumulator, and then inner f as the function. This just works. This is correct. Maybe. Data dot lines minus 2. Let's not use the piping syntax since we're doing this just once. Since there's no actual pipeline here. Okay. So this is our reduce primary. Now we have to do reduce cross as well. This is data. It takes data as an argument. It doesn't take a start because it always starts at the start. Then it does inner f. And this one has to be 0 dot dot data dot columns minus 1. And then reduce of this and something else. And what is something else? Something else is inner f, with data as the accumulator. Okay, and finally we need two coordinates. Two coordinates takes, in our case, it takes an I and a j, and it just returns I and j. This is it. Now if I run it, it should eventually return 136. But it doesn't because undefined function reduce primary. Right, it's not a function, it's a closure. Key cubes not found in cont. So I screwed up passing the accumulator somewhere. Right. The third reduce primary here isn't actually reduce primary, it's reduce primary while. And this also means we don't have to pass the one to reduce primary. So yeah, we don't need a start. We will need a start in a bit. But we don't need a start for reduce primary anymore. We always start from 1. Then the third argument is going to be a reduce while. Right? It's a reduce while data k, yes. And it starts at start, right? It starts as primary plus 1, and it goes to data.lines minus 2. Okay, and here we have reduce primary while. 124. Okay, got something wrong. We have a visualization for this. So we do this on example. Bam. And we clearly see that it didn't move everything. More stuff should have been moved north. So somehow it skipped the first line here. So data is always threaded through, as expected. Location primary cross, I and j. This is correct. Here it goes to data lines. Lines doesn't actually matter because it's this, the lines and columns don't actually change. And these reduces always take a data and then they thread through data. This takes a data, gets a data, takes a data, gets a data, takes a data, gets a data. Oh, it's almost like this shouldn't start from 1. It should start from 0. It should start from 0. I run this and 129. Still not quite, still not right. Not right? It's not 129? No, it's 136. So what's actually wrong? Tilt north, and the original one was called tilt north original. So how is tilt north original different from tilt north? These look identical. Do I have a keynote that shows things side by side? I feel like I do. Grid. Arranges outputs in the grid. Note that the grid does not support scrolling. It squeezes the content. Yeah, fine. So just do grid images or grid to keynotes. So here, let's say this is data. Then we do keynote shorts grid. And we're going to get, let's do this HTML thing. Let's do this HTML call here so that we don't have to repeat it several times. So now we have part 1 tilt north of data viz draw board, and part 1 tilt north of data viz draw board. And the first one is actually tilt north original. And then this takes a second argument, which is columns 2. This did not squeeze the output. The documentation lies. What if we make it 400? Still a bit too big. Let's do 300. Okay. What's different between these two things? Ah, here. So see, this is the correct code, and this is the wrong one. And now we can clearly see that it didn't move these two for some reason. I probably screwed up a -1 somewhere. Right? So here it goes from I+1 to data, whereas, so this is primary, this is cross. So primary goes to data lines -2, which is correct. And then here, there's no minuses. But where does the other location? Here. The other location goes to data lines -2. It should actually go to data lines -1. And now they're identical. And indeed, we get 136. We don't need to print the boards here anymore, because we have better visualization below. Okay, so we now have this kind of monstrosity. And we now need 3 more of them. Tilt, let's do the tilt west. Let's do tilt south first, since that's probably easier to think about. So here, instead of doing this, we now have to start at data.lines -1. Elixir ranges are smart enough that they can go down as well as up. And it goes up to line 1. We don't need to go to line 0 because we can't move anything over line 0. then the cross is going to be what? It's still going to be 0 to columns -1. This is unchanged. And the reduced wall is going to start from 0 to, and it's going to go down. And this one will go down to 0. And then our coordinate function is exactly the same. Okay, so tilt north. Let's actually visualize the original here. And then instead of, this is the visualization and tilted north, let's now see what tilt south looks like. It looks completely broken, so this is clearly wrong somehow. Right? Yeah, this makes no sense. So tilt south. Am I right that that Elixir ranges go down? What happens if I do 9 to 1 and noon to list? 9 to 1. Okay, so this definitely works. Now, here we have tilt south. So we start from data.lines down to 1. Then we do data, and the cross is the same. And here we do start. Start here shouldn't be primary +1. This is the problem. So the reduced primary while is actually going to be -1 here and +1 in the above example. In the north case. In the north case, it's start +1. And this looks much more plausible, but is it correct? So we have 4 things fell down, 2 more things there, this one fell to here, and then this one fell to here. Yep, this is right. This one fell down, this one fell onto this rock, these 2 are now on this ledge. There are 2 things here, and then 1 fell down. Okay, tilt south works. Let's now do the slightly more complicated tilt. Let's say tilt east first. So tilt east. This one's unusual because now the primary is going to be the columns and the secondary, and the cross is going to be the lines. So we go from data columns. Can I just blindly replace this? Can I just blindly swap columns and lines? And then here also change I and j to be j and I. This correct. So here, tilt east. Looks plausible, is it correct? So these 3 fell here, this one and this one fell here, this one fell here, and then another one on top of it. This one fell onto the ledge here. All of these fell here. Yep. This looks right. Okay, so now let's do tilt west as well. And this is just going to be tilt east, but with the ranges basically flipped. So we start with, how did we do it? -1 to 1. Here, this is going to be data.columns -1, and it goes down to 1. The cross enumeration is exactly the same, and then the reduce while, the primary while is going to be from start to 0, from start -1 to 0. This is called west. Here, let's try it out. Looks plausible. So this one fell here, these 3 are here, there's nothing on that row, then we've got 2 on the ledge and 2 on the bottom. Two on the ledge, one on this ledge, one on the other ledge, one on the ledge at the bottom, one fell to the very end, and then two fell onto this ledge. Okay, this works. So now let's add yet one more function called tilt 360. In fact, we can delete our tilt north original, because we know our code is correct. So we're going to now do tilt 360. Def tilt 360. It takes the data as an input, and then it's going to call those functions in a counterclockwise order. So it's going to take the data and then pass it through tilt north, tilt east, no, counterclockwise, tilt west, tilt south, and then tilt east. Right? It's, where is it? North, west, south, east. That sounds right. Now here we just call tilt 360 and see whether we get what they said is correct. Tilt 360. No, here, after one cycle. I feel like we didn't get the right thing. Yeah, this looks different. Is it the same board? It is the same board, but it's a different output. Well, let's do it bit by bit and see what happens. Right? That's the only real way to debug. So, tilt north. Tilt north is correct. Each cycle tilts the platform 4 times so that the rounded rocks roll north, then west, then east. After each tilt, the rounded rocks roll as far as they can before the platform tilts in the next direction. Okay, so let's do more lines here. Actually, the next one is going to be what? I really wish this had this key bindings. The Vim key bindings are not pleasant to use. So tilt north and then tilt west. This is not west, is it? I just screwed up west and east. This looks like east. Really? If I do tilt east, yep, I mixed up west and east. West and east. And here, let's just have the fourth one be tilt 360. Is this correct? Tilt 360. Okay, this looks closer to what they had. After one cycle, on the first 2 lines, we have just one rock at the very end. We have just one rock at the very end. Then on the next row, we have 2 rocks next to the middle edge. Then 2 rocks onto the next ledge. Yep, then 3 rocks. Then 1 on each of the first 2 ledges. Then 1 rock on the sort of middle ledge. Yep, then 4 rocks to the very end, and then a little L shape, reverse L shape at the bottom. Okay, what happens if we run? So we don't need this anymore. What happens if we run it twice? Let's pass an argument to tilt 360. So the second argument here is count, and it defaults to 1. And then we're just going to do this whole thing count times. So this is 1 to count, do enum.reduce, we take data, we don't care about the actual index, we do care about the data, and then we call the 4 functions. So this should still run. And this one should be our after we've tilted twice. So here we go. The first 2 lines have just one thing at the very end. Here, yeah. Then the third line is empty, and the fourth line has just 1 on the edge. Then we have 3 here, 1 on each ledge, 1 on each ledge, 1 in the middle and 1 at the end, 1 in the middle, 1 in the end, 3 at the end. Yep. Then 5 in a sort of stack or in a sort of mound. Yep. And 1 at in the very corner. After 3 cycles, let's try 3 cycles as well. So we have just 1 on the second line and then nothing on the third line. 1, nothing on the second, then 1 in the middle, then 3 on the ledge, then 1 on each of the 2 ledges. Yep, then 1 at the middle, 1 at the end. Then we have this sort of overhang here, and then a Tetris block at the bottom. Okay, so this is correct. But is it fast enough? Because we have to do this a billion times. Let's try it out. So here, so first off, we need a bit of debugging, or we need a bit of progress, let's say. Right, so here, we want the index. If the remainder of dividing the index by 1000 is 0, I'll inspect let's say, the index. Now here I'm going to do, instead of tilt north, tilt 360. Okay, and what if I do tilt 360 2000? Okay, so it does about 1000 per second. So that means we'll need 1,000,000 seconds. 1,000,000 seconds is a lot of minutes. What is it? 1,000,000 seconds divided by minutes divided by 60 seconds per minute is thus many minutes. Divided by 60 minutes per hour is that many hours. Divided by 24 is 11 days. So with this code, we can do it, we can solve the problem in about 12 days. On the example, if we do this on full, it's probably slower, isn't it? Oh boy. Oh yeah, it's way slower. Okay. So our effort, all of the code so far isn't actually wasted because we now know that this is correct. So whatever we do next, we can test against this. It hasn't even completed 1,000 tilts for the full one. What happens if I stop this and then try it again just for a much smaller number, let's say 6. Is it broken or... No, it's not broken, it's just really bloody slow. Yep. So for the full board, we do about one iteration, we would do about 1 second per 10 iterations. So this is 100 times slower than the example. So if we can solve the example to 1 billion in 12 days, we'd need 1,200 days, so about 4 years to solve this for the full. Yeah, that's not good. We can do better. Now, I wonder if this is another one of those caching tricks. I wonder if these repeat. I wonder if the boards repeat at all. I feel like they probably do. How do we test if the boards repeat? Right, so, okay, so here's my thinking here. There's two possibilities. Possibility one is we have to just make a much better tilting algorithm than we currently have. Like our cubic tilting algorithm is, of course, pretty bloody slow. And we could definitely optimize this by using better data structures, by keeping track of where the static cubes are, and then pre-computing something. But doing that would require us to then have special code for north, south, west, and east. Like, it would make everything here much more complicated. So the second possibility is that the boards actually cycle. As in, after a while, the boards reaches a certain state, and then after a bunch more tilts, they reach the same state again. And I wonder if that's the case. And I think the way we can test this is with the example. And how? So when we do tilt, I want to also remember the board state. And really the board state is just our set of rocks because everything else is static. And then if I see the same set of rocks again, that means we've repeated. Okay, so in Tilt 360, let's add some more testing code. Our accumulator is no longer just data, it's also, what shall we call this? History. This is called the history. And then we take the data in the history, and then we'll return new data. And then we want to return new data and history. And then at the very end, we just want to return the data. The history here starts off as an empty map. An empty map. Let's say it's an empty map. So this should still run unchanged. Okay. There's my Tilt 360 here. However, the history does change. The history is going to be mapped put history data.rocks. This is going to be annoying to put in the map, but maybe it's fine because it's Erlang. And IDX. So this means we've seen this particular configuration of rocks before at this iteration. And then here, if data.rocks, no, if, well, case, map.get from data, from history, data.rocks, do. If it's nil, then it's nil. We don't have to do anything. However, if we do get an index, then we print out repeat, seen before at IDX. Okay, we don't have any repeats in the first 69. Bingo. Haha, haha. See? Wait, no, we did have repeats at 10 as well. So repeat, I want to write, I definitely need to see, where is this? Too much code in one place. Yeah, I want to see the current IDX as well. So this is repeat at IDX, seen before old IDX. Repeat at IDX, seen before at old IDX. Okay, so 11, so 4 repeats as 11, then 5 repeats as 12. So really, we don't need to compute that many of these, right? Because this is fully deterministic. So once we're in a cycle, we're always in a cycle. So let's do this on the full example, on the full input. Does this repeat? It does not repeat. That's frustrating. What if I run it for a bit longer? Oh, the other trick here is that maybe it doesn't repeat for a full 360, but maybe it repeats in the middle here, like tilt west, north, south, east. So we'll try. Nope, it repeats. Yep, and it repeats at 110 because presumably they realized that somebody was going to try this, so they put the repeat a bit further in. Okay, so we're almost done then, right? Because once we see a repeat, we don't need... What does it mean? Once we see a repeat, it means we can just look up the next index. It means we can now just do math and then pick out the right thing. Okay, so first thing, we stop this. Then we switch back to the normal example. We don't run it for this long because we know that it repeats at 10, so let's just print out 20 of them. Okay, so now the question is, what happens when we see a repeat? When we see a repeat, we should stop doing... Let's move our tilt 360 function a bit further down so that we don't have to scroll up and down this much. Let's move it here. This should still run. Yeah. Okay, so we are here. We have found an old index. At this point, so we are here. We have not found an old index. This means that we have no choice but to compute this. So we do the new data stuff and continue our iteration. This should still run. No. What did I do wrong here? Oh, here. Okay, now here. So we have a repeat. We have to repeat. We have to reduce. Instead of reduce, we're going to do reduce while. So here we continue in this case. And in this case, we say halt, and I know, let's just say old IDX. Old IDX in history. The following arguments were given to compute load. Right. So here, instead of old IDX, let's just comment this out for a second. Okay. So now here, instead of old IDX, we have to return the actual board that will repeat. That should. How do we do this? First off, we flip with the his. First off, we have to compute the index of count. Here we're going to change our iteration to go from 0 to count -1, since that's easier to reason about. Now here, we want target index. Let's call it target IDX. This is going to be count minus... Actually, no. This is going to be remaining. Where is it? Here. So target IDX is going to be count minus IDX. This is how many iterations we still have to do. Right. So if we're at iteration, if our IDX is 3, that means we've done 4 iterations. So if we had to do 5 of them in total, 5 minus IDX minus 1. This is how many more iterations we have to do. So target IDX is going to be old IDX plus remaining. But of course, this might wrap around. So this has to be divided by something. So we compute the remainder of this and max history. History length. History length is just going to be history piped into what? Map.keys piped into length. Elixir size of a map. Surely there's a better way of doing this. There's a map size function? Really? Okay, then it's map size of history. And then the thing we return, this should still run. Yep. Let's actually print out these things. IL inspect. Actually, we return old IDX here. Might as well return target IDX as well. Let's print out all of the other things as well. So we're currently at IDX. We found a repeat starting at old IDX. We have a history length of this, and then we want to return that target IDX. So we are currently at 10. We found a repeat at 3. Our history length is 3. So if we're at 10 and we want to compute 20, we have 10 more iterations to do. So then this is going to be Target IDX should be... No, it should be 3, so this is not -1. Okay, so now we just have to find in the map the thing that has target IDX. So it's map.find. Because here we need to sort of flip the map. And surely there's a better way than actually computing a new map. Surely. Okay, so let's say history. We pipe this into enum to list. Enum to list. Next we do enum map. We have x and y, and then we're going to return y and x. This is going to be called flipped. It is a bit ridiculous that I'm doing it like this, but... Or is it? And then here we do enum sort by fn of x and y. We sort by the first element, which is now going to be the history. And then keyword get. No, keyword get isn't going to work. It's list key find. List key find exclamation mark, because we can't actually fail on this. Target IDX. Does this blow up? No. Okay, so here instead of all of this, I'll inspect this since there's probably a bug here. Like, this looks very easy to get wrong. This is just a new data. Let's call it final data. Indicate that we are not going to do any more work on it. Not called key find. Alright, key find needs to take a default value, doesn't it? Position. List key find. Receives a list of tuples and returns the first tuple where the element at position in the tuple. Oh. So 0. Okay, this did something. What does this whole thing return? The map set. Because this is not actually final data. This is final rocks. Then the thing we return is going to be data with the rocks replaced by the final rocks. Right. Now if we compute this, why is there a 3 here in the rocks? Because keyFind also returns the index. So this is then fn x and y. We don't care about x, we just return y. Now we compute the load here. Right. Now how do we test this? I think we can test this by just computing the load for a bunch of inputs, can't we? Right, so here we do input is, this is the input. And then we also have here, till 360, let's say history, store history. Here, new history. If store history, do, if we store the history, then the new history is going to be this. Otherwise, we don't store it. Else, it's just going to be history. We're doing this because we know that this thing is correct. The history might not be. So we want to compare tilt360 with history with tilt360 without history. So input, then we do 0 to 20, not 0, 1 to 20. And we pipe this into a new map, fn count. And then we're going to do data piped into this. And here, instead of doing tilt360 it's tilt360 count. So this should print, where's data? Oh, it's called data here. So I'm hoping that this will print 20 numbers. Well, not actually print. Where's the IO inspect? Let's get rid of... There's an IO here, new history. Okay. Let's leave the printfs alone. So now we just... So this is without history. And now we're going to do with history, which is exactly the same thing, except we also pass history is true. Store history to be true. And then we do IO inspect without history and IO inspect with history. And then, okay. And these look like the same things. You can actually compare here. Equals with history. So this should return true. Okay. Now what if we do this? Let's just do it to 100, because why not? True. Okay, so we have tested that our thing works. So now we just need to do the full input. We now need to do the example to 1 billion. Do they actually tell us what the example to 1 billion is? Yes, in the example above, after 1 billion cycles, the total load on the beam support is 64. Okay, so comment this out for now in case we need to do more testing later. So we start with data. Then we do part 1. Wait. True. Ah, I screwed this up. We did not test properly. Serves me right for relying on default values. So here it's count true, count false. False. So there is a bug. Yep, let's do it for 20 because this should illustrate the bug as well. Where's the bug? There is a bug somewhere here at the very end. Huh. Okay, let's also print this out. And let's actually put this into a function. Let's call it tilt many. Tilt many, yeah, tilt many. And the only arguments this are the count and the store history. And then we just take this. And it goes from 1 to count. Yep, and then here we pass store history. And then additionally here we do res is this. I'll put s, let's just say for count inspect res. Yep, and then we still return res because we want to compare it later. But here we do part1 tilt many up to 20 and don't store history. With history is part1 tilt many to 20 and do store history. Undefined variable data. Where's data? Right. This also needs the data. And now all of the repeats and our inspects here are confusing us, so let's comment them out. What's this 0 that is still printing? It's still printing something. Here. Yeah, we just don't need this at all. This is not as helpful as this I'll put s here is not as helpful as I had hoped it would be. So we need to do this afterward. Instead of IO inspecting the two things, let's zip them. How do we zip? We do zip? No, yes, zip. We start with without history, with history. Then we pipe into enum.zip. Then we're going to get, well, actually, and then we pipe this into enum with index. Then here we're going to get without, with, and index. And then we can now print out something nicely. Tilt idx. And it's going to be without versus with. Enumerable not implemented for function. This is right. So here zip is like this, and then here we have an enum.map. Okay, so for the first 10, they're exactly the same because they don't repeat. Then at 10, they start repeating, but then at 16, oh, that's interesting. So they don't repeat perfectly? No, that doesn't make sense. So what happens after 65, 63, 68? 65, 63, 68, and then we have to have 69. And we do have 69 here, but we have 104 here. What the hell is this 104? The 69 is, notably, it's the one at the end. And of course, after it gets to this 104, it goes off the rails completely. What even is this 104? Like, this is the question. Because clearly it's computing the indexes into the history correctly. So at this point, the cycle isn't the full history. That's it, isn't it? Because this 69 here happens to be just before the repeat. So the cycle is So index 10 repeats was found to repeat at starting at 3. The history length is 10, but the cycle length is only 7, not 10. The cycle length is only 7, not 10. So the target IDX here, it's not history length, it's the cycle length, which is history length minus old IDX, right? Yes. So now they repeat and now it breaks here. Why does it break here? So it thinks that 10 repeats starting at 4. No, 10, 3, so this old IDX plus remaining. No, this should be 3. This should always be 3, shouldn't it? What's remaining? We do have IDX here. We have count. We don't have count. Let's also include count in this. What is this? Oh, okay, so 11. We want to find the board for position 11. What we have reached index 10, we have reached board 10, and we see that it actually repeats from board 3. So therefore, it should be 4. So the target index in the history is 1 greater than 3, which is 4. Correct. Okay. And then it starts repeating here, which isn't correct. It should start repeating around here. Or it should cycle back to the beginning of the history here, not here. So target IDX, modulo history length was kind of right. Right, so it's 5, 4, 6, 7, 8, 9. But here 9, this shouldn't be 0. This should be 10. Right, because the history has what? No, or rather, this 0 is sort of fine, but it's not actually 0. It should be 3. This here should start from 3, because 3 is where the cycle starts. And 3 is old IDX, so it's old IDX plus remaining divided by history length. Is it old IDX plus everything outside of... Looks like it. So what did it do this time? It did 4, 5, 6, yes, and then it got to 9, and then key 10 at position 0. Wait, this I will inspect is too far down. Let's put it above here. Okay, so it got to 17. 10 repeats from 3. This 10 is the length of the history. So now it should pull out 10. No, it should not pull out 10. It should try to pull out... what? It should pull out 3 plus something modulo 7. Okay, something modulo 7. The history length here, it's history length minus old IDX. Now it's true. Now the two match. Okay, this possibly works. Let's try to 100, just to make sure we didn't screw up something else. Okay, true. So tilt with history works. We can comment out this IOInspect so that it doesn't make our output look horrible. Yep. Still saying tilt. Oh, it's saying that. Okay, so now we comment all of this out. We have our data, and we try to compute data part 1 tilt many 1 billion. And we are using the history. And then we just pipe this into compute something, compute load. This is taking surprisingly long. Why is it taking surprisingly long? Because really it should get to 10, and once it gets to 10, it should be done. Because I said tilt many. But I don't want tilt many, I want... Right. We don't want tilt many, we want tilt 360. Now this immediately returns 64, which is the correct answer. So now we do this for the full example and for the full input, and we should get the right answer. This will take like 10 seconds to run because it only starts repeating at 100. Yeah, the full input only started to repeat at around 110. Eight 7700. 877700. That's the right answer. You are 1 gold star closer to restoring your snow operations. Okay. So done. Well, this is kind of a mess because everything is solved in part 1. So let's do some cleanup first. The 2 bits of cleanup I want to do is I want part 1 to actually answer part 1 and a new section called part 2 to answer part 2. This is just so that if anyone ever reads this later, well, they don't get confused. So this is part 2. And then for part 1, we just have to do what? We just have to do part 1, read input, full, and then we just have to tilt north, don't we? Part 1, tilt north. And then part 1, compute load. 106648. Let's look at 106648. Okay, so this was part 1, and then part 2. This is going to take 30 seconds to actually run. What else can we do here? Part 1 and part 2 essentially share, well, they share basically all of the code, so I'm not going to bother moving it into a separate section. And this is correct as well. Visualizations still run. Let's get... So I want one more visualization, I think. I want another visualization to illustrate the sort of history cycle. But first, let's see what our final board looks like. So we take full, then we draw it once, then we do tilt 360. Let's do 10. Let's store history. Now this should print out 2 boards. Okay, and now let's do 1 billion. And you know, we should just, we have pixels, we have big screens. We should make our boards bigger. Stop this, and then start again. And the unfortunate side effect of how Livebook is structured, our Livebook is structured, is that it has to re-execute everything from the top since we aborted. But we're going to solve that by branching this off of part 1. So next time, we only need part 1 to fully evaluate, and part 1 is fast. In the meantime, how do we get the history out of this? Well, we do get a history here, so I guess we're just going to have a second tilt 360. No, I know, we can just add the history to our data. Yeah, that's what we're going to do. Okay, here. So this is our original. Can I zoom out? Yes. So this is our original full board, and this is after 1 billion. And I want to copy paste this. I want a screenshot of this. Because this is going to be the YouTube thumbnail. It saved it. This is fine. All right. So let's call this visualization 1. Back to here. I said I don't touch. So here, instead of returning a tuple at the very end, we're just going to append the history to data. This is now going to be data piped into map.put rocks, final rocks, and then map piped into again map.put history. And this is unreadable, so let's split that onto multiple lines. Okay, and now we don't need to do this anymore. And then here where we were passing a cont, this is correct. Is it? No, let's just do the same trick. Map.put, new data, history, new history. Sorry. Here, I was somewhere here. Here I was. Okay, and then here, instead of data, we start with map.put data history empty map. And then this only takes data as an accumulator now. And wherever we have history, here we have a history. This is going to be data.history. And here we have data.history. Here data.history. Here data.history. And here data.history. Now this should still run. Undefined variable history, 180. Oh, we're not actually modifying the history here, so we don't have to change anything. Why was this so fast? Because it's just tilt north, and it's the correct thing. If I wait, and here we actually didn't need to change the old code. The old code was slightly nicer, so let's write it again. Data, and then rocks, final rocks. We're using the map update syntax. Okay, and now if I run this, it should still run correctly. And the advantage now, and the thing we have now that we didn't have before, is that we have the history in the output data. 87700, this was it, right? 87700, yep. Okay, so let's do a new section. New section is going to be called Visualization 2. Actually, History Visualization. This one is going to be called Board Plate Visualization. This one is also branched off from part 1 so that we don't have to compute part 2 and plate visualization every time. Now what do? We do part 1, read input example. Then we do part 1, tilt 360, let's say 200, true, and store the history. Now we get the thing, but also notably, we have this history map. And actually, we need one more bit of information. We need to know where the repeats started. So here, we actually do need the more complicated, the uglier but more versatile syntax. So map.put rocks, final rocks. We're also going to return, we're also going to add cycle start old IDX. You know, we should have cycle, which is between old IDX and new IDX. Right, old IDX and IDX. And then maybe later we'll display some more stuff, but for now this should be enough. So here, we now also have old IDX somewhere in, we should have cycle somewhere in here. Columns, history, lines. Just missing it. Dot cycle. Then fn data and data.cycle. What do you mean part 1 module part 1 is? Oh. V10, okay. Now I want to print a mermaid chart of our history. Oh, this is going to be a really boring chart, isn't it? But not entirely, because we're going to call compute load on it, so it will have some amount of data at least. Okay, so let's print out stuff. Right, so we know that 310, so this means we want to print out, I want a graph that looks kind of like this. 1, 2, 3, 4, 5. It actually starts at 0, doesn't it? 5, 6, 7, 8, 9, and then instead of 10, we are going to have, yes, behold my ASCII art. Behold my ASCII art. Yeah, this is the graph I want to generate. And then also for each of these, I want to annotate it with the actual load. And then also probably highlight the target IDX, the one that we actually want. Okay, so to generate this, we have to do the following. So we have to generate 10 nodes. So this is going to be cycle start, cycle end of data.cycle. Then we're going to do 0 to cycle end -1. Then we're going to enum map to this. And then we're going to print out something, but actually we're not going to print out something. We're going to return a string. And the string is going to be state IDX. State IDX points to, and then here up to -2, let's say. No, up to -1. State IDX points to state IDX +1. Okay, except it's not state IDX +1. Next state is going to be if IDX is cycle n -1, the next state is going to be cycle start. Else, it's going to be IDX +1. We can write this in the more compact form. Forget, is this how you write it in Elixir? Instead of IDX +1, we have next state here. Okay, this looks right. So state 0 to 1, 1 to 2, 2 to 3. And then eventually it gets to 9 to 3. Okay. This looks right. We should call this something, shouldn't we? This is going to be called edges. And then at the end, we want to generate a string that looks like graph pd new line edges that have been joined with new lines in between them. Okay, and now we pipe this into Kino Shorts Mermaid. Syntax error. This is not a single arrow, this is a triple arrow. Okay, this kind of worked, except TD looks horrible. Let's do LR. So we start with 0, 1, 2, 3, then we do this, and then it loops back to here. What did they call it? 3 cycles. So let's call this cycle. Let's call this, like the first one should just be called, let's call it cycle, doesn't matter, good enough. In fact, let's call it C. Being ambiguous is actually a virtue here. Yes, C0, C1, C2, it looks back. Okay, but now I actually want to annotate this with the load on the north thing. With the load on the north side. So in order to do that, First, I want to have the reverse history here, the flipped history here. So, do I need the flipped history? I do need a flipped history. Flipped history is going to be data.history typed into enum map. So this is going to take the rocks and the index, and it's going to return the index and the rocks. And then we're going to turn this back into a map with into. Right. And now here I can get the rocks for this particular index by doing flipped history map get. I can do map get a flipped history and IDX. And now that I have the rocks, I can compute we can compute the load by doing part 1 compute load, and we have to give it the data. But where the rocks are, the rocks the historical rocks from here. And then here, where do we include this information? We can't do it here exactly, so we need to have a second one of these enumerations. Let's for now include it on the edge, even though that's incorrect. Let's just see that it works. Missing an end. Okay, now this 104 should actually be above C0, but so our code works. We just need to use the mermaid syntax to define our nodes ahead of time. So we need to use this syntax. And we can actually do that, and it even saves us from having to do this this lookup. So enum.data is going to go into enum concat. And then we're going to do 2 enums here. This is the second enum, these are the edges. And then there's also going to be something here that gives us the nodes. In fact, let's name this, because this is hard to read. Edges is this. Then we return nodes and edges. This has to be here. And then flipped history, this whole flipped history thing is going to be how we compute the nodes. Nodes is, we take the history, we go through rocks IDX, and then instead of just flipping, we compute the load. We compute the load, yes. And we compute the load by doing this. We have the rocks, bam. No longer need to do that lookup there. Now here we can delete this. And here we're going to output C IDX. And then in square brackets, in load. Now we're going to do C IDX again. Colon and the load, yes. And this needs to be escaped. No, this is no longer called edges. This is going to be called just lines. Lines is fine. Okay. Oh, and this is not, this is cycle. Let's just go back to calling it Z. Okay, so C0 is 104, 87, 69, 69, 69, 65, and so on. I want one more thing. I would like to highlight, the actual result. And the actual result is here. So this is the cycle. And then let's have another map put here. Final IDX. This is target IDX. And I want to bold out the final IDX. And I have to do that here, I believe. Right? Yes. If IDX equals data.final IDX, do something. Otherwise, do this. And the something is very much like this one, like this, except we're also going to add a strong here. Does this work? No, this did nothing. But I should be able to do a span. Style. Color. Let's just make it red to make it visible. So this is the result, 69. Read input example. Let's do 1 billion. I think 64. Yeah, 64. So this is the result. Now instead of color here, is it called font weight? Bolder? Yes. Okay, so now we have a display for our example. Oh god, and if I do this, so I'd like to do this for the full thing, but if I do it for the full thing, we know that it only repeats after 100. So this is going to look kind of like crap. Flowchart, sequence. Do we have something that is more timeline? No. I was hoping we'd get a better graphing algorithm, something that can display more things. Oh, what's this? It is also possible to declare multiple node links in the same node. This ain't helpful. Okay, this is to define subgraphs. All right, what happens if we do this for full? I'm probably going to regret this, or rather it's going to look like crap, but let's see what happens. Actually, while we're at it, how did they do the thing where they change the color of a full node? This class stuff something. Here, where we do our concat. Flatten. Surely flatten exists. Is it list.flatten? List.flatten. And here I also want to do this. This is not called some class, this is going to be called ha ha ha. Okay, yeah, that doesn't work. Final. And this is going to be fill red, green, blue. Let's do CCF. Let's go back to example. And here, instead of this style thing, we need to do double colons, I think. Right? What's the syntax? So it's triple colon. Triple colon. So, final? No. Are the triple colons after the text? Yes. Okay, but that's not visible enough. So I actually wanted green. And this should be 9 then to make it stand out more. Okay. Okay, so I think we're going to leave this for with the example. And then play visualization here. Let's do this again for the example as well. I'm doing this because I want something nice to post on Mastodon and have a nice thumbnail for the YouTube video. Okay, so this is our original example board, and then it becomes this. Let's take a screenshot. And then here. And then the way we got to that board is by following the cycle. So we start like this, and then we loop back. We get to here. And I'm not wrong that 64 was the right answer, was the example answer. Yes. Okay, I want another spectacle. Let's grab this as well. Save. Okay. And with that, I think we're done. Yeah. So, review time. Parabolic reflector dish. Today's problem, yeah, this was pretty interesting. We had a board and we had to run a bit of a simulation on the board. Actually, computing the simulation wasn't all that hard, although there were a few edge cases because, well, we have to work with actual numbers, so there were off by 1 errors. But once we did that, the problem with part 2 was that we had to run the simulation 1 billion times, and the simulation was slow. However, we noticed that the simulation repeats. Yeah, the simulation has cycles, so after a while the simulation gets back into a previous state, and once that happens, we just keep moving around the same cycle again and again. We have a cycle, we actually have a cycle to display, yeah. So after we get to the third state, we then start looping through this cycle. So in order to compute the billionth iteration, we don't actually have to run any more simulations, because we know they're going to be somewhere on this cycle. We just have to do a bit of arithmetic to figure out where on the cycle exactly. And once we have that, we could just return it and yeah, and then we're done. Yeah, so nice problem today. What do the stats look like? How are people doing? Day 12 is still the day that seems to be causing people problems. Like, people aren't going back to solving part 2 once they've given up. But yeah, today is going fine. It's about the same number of people as yesterday, so we haven't really lost any more contenders. All right. That's it for today. Thank you for listening, and see you all tomorrow.